Okay.
Thanks very much. I'd like to introduce our second speaker, Ming Yuan from the Georgia Institute of Technology, who's going to talk to us on sparse regularization with multiple reproducing Karnel Hilbert spaces.
Thank you very much. So today I'm going to talk about actually issues related to a class of sparse regularization problems using the tool of reproducing Karnel Hilbert space. Try this one. Yeah, so this is the outline of my talk. Basically, I'll start by introducing this general framework for sparse regularization, as I will show you many of the common methods like lasso, group lasso, or casu. They can all be formulated in this unified framework. And of course, having such a unified framework allows us to see the connection between these different methods, and also it gives rise to ways of exploring sparsity in other contexts as well. And after briefly talk about the computational issues involved in this general class of sparse regularization problem, I'll focus on the theoretical properties. In particular, I'll discuss the estimation problem when the dimensionality is really much higher than the sample size. And if time allows, I'll also briefly talk about the selection part, which is more related to Nikolai's talk yesterday. And so, So basically the problem we're interested in here is this general prediction problem. We have an input space X and output space Y, and our goal here is to learn a map from your input space to output space. And the main goal here, of course, is in the future when you get to observe an instance in the X space, you can make a prediction using fx. And of course, to measure the goodness of your prediction, we use this loss function. So as I denote here, L. And so L measures the closeness between Y, which is the true label, and your prediction fx. And of course, naturally, our goal is to recover this target function often is given as the minimizer of this so-called risk function, which is nothing else but expectation, the population expectation of your loss function. So in practice, of course, one thing I want to mention is this minimization is taking over all the measurable functions from your X space to Y space. So in practice, what we do is instead of minimizing the population expectation, we replace it with the empirical version. So we minimize the empirical risk. And of course, another thing is we cannot minimize over all the measurable functions. So usually we take a smaller subset of functions. This essentially amounts to the problem of statistical modeling. For example, if you consider linear regression, you would choose this functional space to be all the linear functions. But still, in many problems, we run into overfitting problem if you have, say, a high-dimensional problem. So often we put a penalty here, leading to the so-called regularized empirical risk minimization. So this is the general problem of interest here. And in particular, we are going to focus on the following sparse regularization problem. So we are going to model the functional space to be a linear span of the union of a set of reproducing Karnel Hilbert spaces. And each of the component Hj is a reproducing Karnel Hilbert space. Essentially, it's just a normed linear space when the following property actually is one-to-one correspondence between this space and the so-called reproducing kernel, which will become handy later in the next couple of slides. But so basically, what we have is each component is a normed linear space, and our functional space is the linear span spanned by the union of all these reproducing Karnel Hilbert spaces. So why are we interested in this kind of space? If you look at a typical member from your functional space, it admits the following additive representation. So essentially, your function f from your functional space H can be written as the sum of f1 all the way up to fp when fj coming from the respective reproducing Karnel Hilbert space. So this is exactly what we have in additive model. And throughout this talk, actually, I'll show that many other methods can also be formulated in this way. But throughout this talk, you may think of additive model as a canonical example in understanding what's going on here. And if we look at this functional space, if we define this functional space in this way, then you can think of the possible norms that we can equip this function with. That's why we want to have a reproducing Karnel Hilbert space as for each of the component space, because then we can define its kind of L1 type of norm. So since f can be represented in this additive form, essentially what we can do is we can define a norm in your functional space by taking the sum of all these reproducing Karnel Hilbert space norms. But of course, the additive representation may not be unique. So what we need to do is we are going to take the minimum of all these sum of reproducing Karnel Hilbert space norms. And you can check, well, this can be verified, this is indeed a norm defined in this linear functional space. And throughout this talk, we are going to focus on the following problem, the sparse regularization type of problem. Essentially, it's very similar to the idea we have in Nasu. Basically, we want to explore sparsity at the reproducing Karnel Hilbert space level. So since we have this L1 type of norm defined, so it's only natural, we use this L1 type of norm as your penalty, and leading to the so-called, this type of sparse regularization problem. So basically, we can immediately say many of the common methods actually can be formulated in this way. Maybe not the best way of formulating these things, but nevertheless, they can be formulated in this way. For example, you can think of each of the component space to be one-dimensional. So this is essentially linear regression. And in this case, we end up with Nasu. Or we can have this each reproducing Karnel Hilbert space instead of being one-dimensional, rather being finite dimensional. This gives group Nasu. Or in the additive model case, for example, then we can take this functional space to be the functional space for a particular variable. And for example, it can be a Sobolev space of order n. So in this case, we end up with the so-called Kasu. And of course, having this unified framework also gives us ways of exploring sparsity in other contexts as well. So for example, you can think of partially linear model, which basically your regression function has two components, the linear component and non-parametric component. So essentially, you can have this combination of Nasu and Kasu for this purpose. And also, you can deal with varying coefficient model. So in varying coefficient model, in essence, is still a linear regression model, but allow the coefficient may be a nonlinear function of another variable. So in this case, you can also define this kind of L1 type of sparse regularization. So generally, all these methods can be formulated within this unified framework. And of course, one advantage is it allows us to study the properties of these seemingly different methods in a more systematic fashion. So another example, which is seemingly a little bit different, is this so-called multiple kernel learning. So as I mentioned, we are modeling each component space by reproducing Karnel Hilbert space. And there is essentially a one-to-one correspondence between your reproducing Karnel Hilbert space and the reproducing kernel. And the reproducing kernel is nothing else but a positive definite bivariate function. And this, in a sense, reproducing kernel, in a sense, can serve as a similarity measure in your X space. But if you think about the ideal prediction, we are inferring the similarity in Y space using the similarity measure in your X space. So having a good measure of similarity, of course, can help you get a better prediction. So this is essentially the idea. So many people prefer to think about choosing the kernel in order to get a better prediction. And oftentimes in practice, we may get different sources of information regarding the similarity in X space. So if you have many different similarity measures, essentially you can think of you have many different kernels. And what you can do, of course, is to come up with an intelligent way of aggregating all these kernels so that you can have a better prediction. And this is exactly what people are doing. But one thing we want to keep in mind is your kernel, by combining these kernels, you want to ensure the positive definiteness of this kernel function. And one natural way of doing this is to consider a convex combination of all these kernels. And so often what people do is they just go directly to the last line here. So they minimize the regularize the empirical risk, but not only with respect to a function, but also with respect to a kernel over the convex combination of all these kernels. And this is exactly related to our formulation, because if you think about our L1 norm defined over this functional space, as I mentioned, there is a one-to-one correspondence between this reproducing kernel and functional space. So if you think of it in this way, then essentially the L1 norm we just defined is nothing else but the minimum of all these reproducing Karnel Hilbert space norms. And this norm, each norm corresponds to a possible kernel which falls into this convex combination of the existing kernels. So essentially this seemingly different framework, which is kind of active area in machine learning, essentially can also be formulated in our context. And also an advantage here is this also tells us that by using this kind of technique, using this kind of L1 type of penalty, essentially you may also lead to a sparse representation of all these kernels. Rather than combining all these kernels, you are only focusing on a smaller subset of kernels. So these are the general framework. So in the next couple of slides, I'll just basically talk about a couple of strategies that you can use for tackling this general type of sparse regularization problem. So the first type of strategy is kind of backfitting type of algorithm, which oftentimes referred to as a coordinated descent type of algorithm. So the essential idea is as follows. So our goal is to learn a prediction function. And of course, as I mentioned, it admits this additive representation. So equivalently speaking, we can also minimize over these additive components rather than the whole function itself. If we think in this way, then essentially we can do this type of backfitting by updating each component one at a time. And this is exactly the main idea behind the coordinate descent. So at each stage, we just minimize with respect to one component function. And in many cases, particularly of low-dimensional problems, like in lasso or group lasso, there is closed-form solution for this component update. So it can be done very efficiently. And in more general context it has also been discussed in a very recent paper by Friedman et al. And so this works very well for low-dimensional problem. But in high-dimensional problem, well, this may be a little bit more, we may not have a closed-form solution. But in this case, what we can do is, if we can use this so-called representative lemma, which works if your loss function L here is convex in terms of your predicting function f, and which is often the case in practice. So the representative lemma basically says your solution, even if you don't have a closed form, your solution has to be an n-dimensional thing, which is a linear combination of all these representers. And since your loss function is convex, so essentially this becomes a convex program in terms of all these linear combination coefficients. So you can solve them. So the bottom line is at each iteration, you can update each component, and then you repeat it and to get a final solution until certain convergence. So this is one type of strategy. An alternative type of strategy is actually very popular in computer science, but recently was adopted by Lin and Zhang in the context of Kasu. So the main idea is as follows. The method I call augmented oscillating algorithm. So the main idea is as follows. We're trying to estimate this function f. So instead of just minimizing over this function, I introduce another variable. I minimize over both variables. So in a sense, you may think, well, I increase the dimensionality of the optimization problem, so it's going to be a harder problem. But rather, by introducing this variable, what we are going to do is, again, an iterative algorithm. So giving one variable, we solve for the other. And the main purpose of introducing this new variable is in order that for giving one, updating the other is simpler. So this is exactly the case in our context here. What you can do is you can introduce this so-called theta variable, and this theta variable comes in the following form. So recall in the original sparse regularization technique, what we did is the penalty we are putting in is the sum of the reproducing Karnel Hilbert space norms. And here, by using this theta, we can raise it to the square reproducing Karnel Hilbert space norms. And you can show actually for some combination of lambda 1 and lambda 2, it leads to exactly the same solution for f hat lambda. So what you can do here is very simple. Now I update f and theta just iteratively. And given theta to update f is relatively simple problem. The main thing is because of the representative lemma, as I just showed you. Now the representative lemma in this context actually is a little bit more powerful than the previous one, because it not only gives you an estimate for all the functions, but for the whole function, it also gives a representation for each of the component function. And even better, if you think about this, if you look at this representative lemma, it's a relatively low dimensional problem rather than you have a representative lemma for each component, because all of these components, they are up to a scale by theta j, and then it only depends on the same scaling or the same linear combination coefficient alpha I here. If you compare these two formula here, in coordinate descent, we have this representative lemma, which is a linear combination of all these representers, but this linear coefficient can be different for different components. But here, these linear coefficients are common across all components. So anyway, you solve this n-dimensional problem, getting this linear coefficient, then you get an estimate for each component. And what you can do is you plug it back to objective function and update for theta. And now it becomes much easier because now this is just, well, not necessarily much easier, but now becomes a problem in terms of theta, and generally this is a convex problem. The main reason is as follows. The first term, the loss is convex. The second term, if you just by its look, it's not convex because it involves theta inverse. But because your fj involves a factor of theta, so essentially the second term would be a linear function in terms of theta. So essentially this is a convex problem and it's still solvable in principle. So while we're not showing any numerical result, actually basically I just want to give a high-level comparison between these methods in practice. So essentially, both algorithms are kind of iterative methods. And for coordinate descent, if you use this kind of method, essentially what you are going to do is for each iteration, you update each component one by one. And for updating each component, the problem of the dimensionality is either sample size n, well, that happens when the dimensionality of your reproducing Karnel Hilbert space is bigger than n. Then you can use representative lemma to reduce it to an n-dimensional problem, or it can be just a dimension of the reproducing Karnel Hilbert space. So we solve it p times. This is for coordinate descent. For augmented oscillating algorithm, we need to, for each iteration, we update f once, which is n-dimensional problem, and then we update theta once, which is a p-dimensional problem. So in this sense, for each iteration, it might be appealing to use augmented oscillating algorithm, but the first one, actually coordinate descent, in many cases works even much better than the second one for a couple of reasons. The first reason is sometimes, particularly in the case of lasso and group lasso, as I mentioned, you have closed form solution, so the problem is much simpler. And this is for one thing. And another thing is because both are iterative algorithm, it depends on how fast the algorithm converges. And my experience is for low dimensional problem, generally coordinate descent works much better than the second one. But the second one in high dimensional problem, not necessarily it works better than the first one. It's just it's more manageable, more feasible in practice. And of course, depending on your context, in some cases you can devise specialized algorithm to speed up the algorithm. So this is just a brief mentioning of the computation. And mainly I will be focusing on the theoretical properties here. So first I'll discuss the estimation property of this kind of sparse regularization. So before I talk about the technical details, well, I'll first briefly mention the main idea of the result. So essentially this is kind of like an oracle type of inequality we derived here. So we want to quantify the performance of f hat. So what we are going to do is pretending that we load the true function, we first construct a very good approximation. And then we compare the performance of f hat and this approximation. So first of all, let's introduce this approximation. And we require a few properties of your approximation. And a couple of things we would require. The first one is the smoothness. And the other one, of course, has to do with the dependence among these functional spaces. So first of all, we need a few measures of the function of dependence for these functional spaces, of course. And we know this is relatively simple. This can be done relatively simply if each reproducing Karnel Hilbert space is just one dimension, because this is just a linear regression. And the dependence essentially can be measured by the largest and the smallest eigenvalue of your gram matrix. And so this is for one-dimensional case. And when you move to functional space, what we are going to do is we are going to take one function from each functional space. And so we can construct the gram matrix in a sense. And we take the largest of all these largest eigenvalues and take the smallest of all these smallest eigenvalues. And we use this as a measure of how dependent or these reproducing, well, not necessarily reproducing Karnel Hilbert space, just generally these functional spaces are. And also we need another measure which measures the correlation just between two sets of functional spaces, which naturally we can use canonical correlation in a sense. So this is the dependence measure among these functions. And another thing is the smoothness of your oracle of this kind of good approximation. And to understand the smoothness, we need a little bit more information regarding more properties or regarding reproducing Karnel Hilbert spaces. But nevertheless, well, the simple idea is as follows. If you think about your functional space is just a set of smooth functions, what we are looking at here is a smaller subset of these functions, which tends to be smoother than a typical example in your functional space. So how do we characterize the smoother? Then we appeal to this spectral decomposition. And of course, one thing I want to mention is this spectral decomposition generally exists under very mild conditions. And so essentially recall we have this reproducing kernel, which is a positive definite function. And you can think of it as a positive definite matrix. So then you can do eigenvalue decomposition. And essentially this is what we can do here. And the rate of the decay for this eigenvalue really characterizes how smooth the function in these spaces are. And so essentially the correlation actually is given by this inner product I gave in the second line. Essentially the inner product, well, you can think of the inner product between f and phi k to be just the Fourier coefficient for this function. So essentially what we're going to do is the inner product can be defined in this way. It's kind of, at the downstairs we just have this lambda k here. And to define a smoother subsite, essentially, instead, well, for a typical member, well, for a typical member in this functional space, essentially what you want is for this series, instead of dividing by lambda k squared, divided by lambda k to be convergent. And rather, we're looking at a smoother subsite, so we want this lambda k squared divided by lambda k squared to be convergent. So this is basically what we did in order to describe this oracle function. So basically, our oracle function admits similar formulation as a typical function in my functional space. It admits this additive representation, but rather than asking each component function to be just in your function original reproducing Karnel Hilbert space, I want each component function to be the smoother subsite in your space. And so this is how I define a smoothness. And also, we define the supporting site of this function because recall we are doing this sparse regularization. So we define the support of this function to be the reproducing Karnel Hilbert spaces whose corresponding component in this F is non-zero. So this is just like in variable selection, this coefficient is non-zero. So this is the supporting site. And then these are the K assumptions here. So we want some sort of dependence measure that kind of characterize this approximation. And essentially is characterized by the supporting site. So we look at this quantity here. This quantity can be looked at as two terms. The first term is the largest eigenvalue divided by the smallest eigenvalue. So basically, this measures the dependence among the spaces that are the supporting set of your function. And so basically, this tells you that I don't want the dependence for the supporting set to be too much. And the other component is 1 over 1 over minus log square. Log square, recall, is canonical correlation between the supporting set and the non-supporting set. So basically, this tells you I don't want the supporting set to be too much dependent with the non-supporting set. So this condition tells you that for this approximation, for this oracle function, what's going to happen is I don't care about what's outside your supporting set. I care about what's inside your supporting set and what's in between your supporting set and the non-supporting set. So this is basically the condition for dependence. And we also want the second condition. Actually, this is rather than a condition, this is basically the framework we are working on. As I mentioned, we focus on this additive type of model. So if you look at this condition, essentially it tells you each component of your sparse approximation essentially is kind of like a Sobolev type of space. Because these eigenvalues, they all decay at the rate of k up to minus 2 beta. So it's kind of beta order smooth. And so one last thing we would lead is recall we have this function, each component falls into this smoother subsite. And so of course we want to quantify how smooth this is. And one quantity you can use for each component, of course, is to take the ratio between these two things. So if it's very smooth, then this is going to be a constant for each component. But if it's not very smooth, it's more or less lie on the boundary, this is going to be a big value. And we average over all these non-zero components. So after we're defining this oracle function, then we're ready to show this main result. So the main result is under one condition, which I will come back in just a like slide. Basically is if I assume indeed that your sparse regularization gives you a sparse estimate, and in the sense that its L1 norm is bounded by, say, a constant. And then essentially what you can do is you can choose a tuning parameter which is large enough so that you have the following bound with probability 1 minus p up to minus a. So recall we are considering high dimensional problems, so this p tends to be big. And 1 minus p up to minus a essentially is just probability 1 in a sense. So let's look at this inequality here. Actually on the left-hand side, we have two things. The first thing is the excess risk. So the excess risk basically is the risk minus the minimum possible one. And essentially, if you think about in the regression case or L2 loss, so this is just the square, basically is the squared L2 norm between your f hat and the true f star. So basically, we bound the excess risk. And then we have the second term also bounded. As I mentioned, for your oracle function, we have supporting set, we have non-supporting set. Actually, this is kind of related to Nikolai's talk yesterday. It's not always guaranteed we're going to identify the supporting set. We're going to have something outside of the supporting set. But this bound basically tells you we also have a control on how much we have outside of the supporting set. So basically we bound both things. And on the right-hand side, which is the bound, the first term is only natural, which is the excess risk of your good approximation, your oracle function. And the second term may take some time to really understand what's going on here. Well, you can think of in the situation, say this D really is the cardinality of the supporting set for your oracle function f. You can think of in a situation when you know that actually your true function is really sparse in the sense that D is just finite. Then the first term is of the order 1 over n up to 2 beta divided by 2 beta plus 1. So this is essentially the optimal rate of estimating a long parametric function. And the second term we will come back to in just a little bit. The last term actually is also very interesting, is log p over n. So this term basically tells you this term can go to 0 as long as log p is of order smaller than n. So before we take a careful look at this result, let's just briefly mention this assumption we made in the beginning, which is your sparse regularization estimate is indeed sparse, which shouldn't be that surprising because as long as you increase your regularization parameter, you can always ensure sparsity in this sense. But the problem here is we want to have a condition that's compatible with our condition here because we want our regularization parameter to be of this order, which is square root of log p over n. So basically this result basically shows this is possible. As long as you have a regularization parameter of this order, you can always ensure that your estimate is sparse with very high probability, and essentially the same probability, which is 1 minus p up to minus a. So essentially this assumption, basically this slide shows this assumption is okay. So this is the main result. Let's first look at let's take a careful look at what it means. So let's take a look at the excess risk because our bound has 2 terms. Essentially we can just take the second one off because it's positive value. So let's rearrange the 2 terms a little bit. Well, we rearrange in the following way so that actually one thing I want to mention is let's again, it's probably instructive we consider the situation when the true function is really sparse. If your true function is really sparse, in order to find the approximation, I don't need to find a very long sparse approximation. We can find a sparse approximation which just share the same sparsity, same supporting set of your true function. So if this is the case, D has nothing to do with your approximation. So let's arrange these 2 terms together because it has nothing to do with your approximation. Rearrange the other 2 terms together because it has to do with your approximation. Because this holds for all the oracles, all the approximations, so it doesn't matter, we take a minimum of all of them. So now essentially it becomes approximation problem. We try to find a smooth approximation to a true function. So now suppose your true function I have low preference or low prior knowledge is how smooth the function is. So essentially I need to take the biggest possible, not the biggest, the smallest possible approximation error for a general function in your space. And essentially you can do the calculation. The approximation error is of the order d multiplied by lambda. And this is actually a little bit surprising because if you think about lambda, we have this condition, which is lambda has to be at least of the order log p over square root of log p over n. So if you think about these things here, the last term is going to dominate the second term. So essentially our bound will consist of 2 terms. The first term is still kind of like this kind of usual convergence rate, and the second term is d multiplied by square root of log p over n. And if you think about a situation again, think about a situation when d is fixed. Clearly the first term is going to be smaller than the second term. So essentially what we are going to end up with is your excess risk is bounded by this term, which is of the order log p square root of log p over n. So this is a good news on one hand, because basically it tells you, just like in the parametric case, as long as log p is of the order smaller than n, sparse recovery is possible. So although you are moving from parametric situation, say in linear regression, which we already know that as long as log p is of the order smaller than n, you can have sparse recovery. From moving from linear regression to long parametric regression, still we have this property. As long as log p is of order smaller than n, you can still do sparse recovery. So this is good news. But on the other hand, we also have a piece of sort of bad news. Because if you look at the rate here, the rate is of the order square root of log p over n. if you think about the situation when p is finite, we know the parametric rate is 1 over n, and the long parametric rate actually is n up to minus 2 beta divided by 2 beta plus 1. The difference, in a sense, is not that big, as depending on the smoothness of the function, of course. But if you look at the situation when p is really big, what we are getting here is, in the parametric situation, typically in linear regression, you get log p over n. But in non-parametric regression, you get a square root of log p over n. So the question here is, whether or not this is indeed the optimal rate, because what we are getting here is kind of upper bound. So for this purpose, of course, in general cases, it's a little bit harder to understand what's really going on. So we look at a much simplified situation, which is just a sequence model. So in this sequence model, what you can think of is this theta kj is, say, for example, the J's Fourier coefficient of your kth component. So essentially, you have a sequence model like this. And of course, to mimic the situation we have before, you can think of the situation when this theta k, what is Fourier coefficient, has this kind of Sobolev type of class. And then in this particular case, what you can do is we can still apply this L1 type of regularization. And basically, you can formulate in exactly the same way as we discussed before. And so we look at the situation when p is of the order, say, exponential of n up to gamma. And again, we consider a very sparse situation, which is when d is fixed. So in this situation, we can really show actually among all these Fourier coefficients, such that actually I didn't state the condition here, the supreme is taken over so that each component comes from this Sobolev ball on one hand, and on the other hand, they are only at most d non-zero ones. So this is just the typical ones we have in the previous, well, it's very similar to what we have in the previous slide. Essentially, we have a regression, but we know they are only up to d non-zero ones. And each one of them, for these non-zero ones, typically they are just this kind of Sobolev type of function. So essentially what you get is, no matter how you tune it, even if you choose the optimal lambda, in the worst case scenario, or if your theta is really just a typical example from your space, then you get the following bound. When the probability turns into 1, essentially, basically this tells you, essentially this guy is going to be of the order just a square root of log p over n. So on one hand, this basically tells you the bound we derived in the previous case, which is more general, is probably more or less optimal. But on the other hand, it invites more question. So one significant question here is, if you think about the setup here, well, the basic setup is we have this Sobolev space of order beta. But if you look at the rate, beta never appears. So this is actually a very interesting thing, because if you think about when p is finite, clearly the smoothness matters. But when p is really big, it seems that the smoothness doesn't matter. So it has to be a transition between finite to infinite. So to this end, we look at relatively smaller p's. Say, for example, what happens when p is of a polynomial of n. So in this case, we can derive a similar bound, but now it becomes evident, actually moving from linear regression to non-parametric regression, actually something different happens. And we have basically this two-regime situation. So essentially what we get is the same kind of quantity. We are measuring how, well, even if we optimally tune this function, how bad we can get, well, what's the upper bound for the convergence rate. Essentially we get this function phi here, which depends, of course, on gamma and also sample size. And it turns out it has this two-regime situation. It depends on whether or not your p is smaller than square root n. So if it's smaller than or equal to square root n, the optimal convergence rate in this particular context, the Gaussian sequence situation, the optimal rate we are going to get is essentially, well, it essentially depends on gamma. So basically what's going to happen is when your p is really not that big, increasing p, your convergence rate decays. So you estimate getting worse and worse by increasing p. But at a certain point, and this point is exactly when p equals to square root n, then it doesn't matter anymore, the smoothness, the beta level occurs. Then essentially you get a log p over n. And actually it's interesting to look at the situation when gamma equals exactly to 1/2. Then you can do some simple calculation. Essentially on top we get just a square root n. Well, 1 over square root n, I'm sure. So you may ask what happens between, well, square root n and a little bit bigger than square root n. Actually in that case, you don't have this tight bound on at least we haven't got this tight bound at on one hand. And on the other hand, well, the difference here between the two is just the square root of log n. So these are essentially, excuse me. So this is basically a picture shows how this convergence rate is affected by the dimensionality, given that, again, we're talking about a very sparse case, which is D is finite. So essentially, there's this interesting phenomenon. On the left-hand side, we have in the polynomial situation, so when P is of, so on the x-axis, I have the gamma, which is n up to gamma. So on the x-axis, we have this gamma. And on y-axis, we basically have the convergence rate measured in terms of the ratio between the two lateral logs, between the squared error and the sample size. So essentially, in the very beginning, while moving from finite to square root n, we see a linear drop. And once you reach square root n, the change is actually it becomes stable there. But of course, once you increase your dimensionality more aggressively in terms of exponential n up to gamma, then you still see this drop. And essentially, essentially you can still get a consistent estimate as long as log p is of order smaller than n. So of course, one thing we want to look at here is exactly what's the cause of this phenomenon, this two regimes phenomenon. And we know that in the case of linear regression, actually we know that the optimal rate is log p over n. And now we know in the infinite dimensional problem, which is long parametric regression, is square root of log p over n. So just to make sure that this is indeed a problem caused by infinite dimensionality, so we look at the finite dimensional problem, which is kind of in between Lasso and the long parametric one, either Cassou or multiple kernel learning. So we look at this group Lasso. So in this case of group Lasso, basically each one of your reproducing Karnel Hilbert space is of finite dimension, or less than one dimension. So your finite dimension, you can also interpret it in the sense that, well, you have this eigenvalue decomposition, but except for finite eigenvalues, all the others are 0. So it can be derived using the same machinery we have before, the following bound. So the only difference actually occurs in this term here. Recall in the long parametric situation, we get something like 1 over n up to 2 beta divided by 2 beta plus 1. So now in this case, what we are going to get is dv divided by n. And this d, again, is the sparsity of your approximation, and v is the maximum dimension of your groups. So because this is finite dimensional problem, the group Lasso, so v is basically a finite value. And so for the second term, this is what highlights the difference between finite dimensional problem and an infinite dimensional problem. Recall, if we go back to this long parametric situation, we also have this approximation error. And as I told you, actually this approximation error in the long parametric situation is of the order d multiplied by lambda, and which is probably familiar in the case of, say, you just do long parametric regression. If you do smoothing spline, the order of the bias is of the order lambda in a sense. And so in this case, if we move to finite dimensional case, this approximation error actually can be improved. It's going to be d multiplied by lambda squared. So that makes a huge difference between your lambda, because your lambda is of order square root of log p over n. So by square it, we still get log p over n. So essentially, this is what we are going to get. And it's exactly in parallel to what we know for Lasso in linear regression. So your access risk, suppose you consider the L2 squared L2 norm. So your access risk here is of the order essentially log p over n, of course multiplied by d. And also we have a control on what's outside your supporting set, which is of the order d multiplied by the square root of log p over n. So I think, well, probably I have some time to briefly talk about a more classical issue, which is variable selection type of thing. So essentially, it's kind of like very much related to what Nikolai was talking about yesterday. So he was focusing on the case of linear regression. So under what kind of conditions L1 type of regression will be able to tell you exactly which one is your supporting set, which one is in your supporting set. So basically, what we are looking at is the problem which I stated on the top. So we want what's outside your supporting set to be estimated by exactly 0 when the probability tending to 1. And we know, actually, in the case of linear regression, it's already identified by many authors. So there is a condition only under which you can have this kind of this kind of behavior, which is you estimate everything outside your supporting set by exact 0. And so in general, actually, you can derive similar conditions for the more general terms using the reproducing Karnel Hilbert space. And essentially what's going to happen is as follows. So recall, we have a supporting set, we have a non-supporting set. So what you are going to do is, I take one function from your non-supporting set. It can be any linear combination of the functions from your non-supporting set. And then I take one function from each reproducing Karnel Hilbert space in your supporting set. So basically, I have a linear regression problem here. I regress the one you get from a non-supporting set to the basis functions you get from this supporting set. I do a regression. And the main idea here is, basically this tells you, in essence, what this condition means. This condition really means that I don't want to exaggerate the L1 norm by doing this linear regression. And this is basically the states. So this condition, although it looks a little bit complicated, but essentially this is what it means. So I project any function from your non-supporting set to a supporting set, and I don't want to exaggerate your L1 norm, because otherwise, since we are minimizing this thing related to L1 norm, I can always take something in your supporting set and compensate from outside your supporting set. And so this is basically the condition we get in general. And so in the last slide, I just want to briefly talk about, is it possible that in a sense, it's a low-dimensional problem. If you really have finite p, is it possible that we can improve upon this L1 type of regularization? And now we know in the linear regression case, there are a couple of tools we can use. You can use SCAD, for example. You can use adaptive lasso to make this thing, in a sense, to get rid of this condition. But in this case, these two methods seem to be, may not be trivial to extend these two methods in the current context. For SCAD, the main problem is SCAD is a non-convex penalty. If it's a non-convex penalty, your represent lemma doesn't hold anymore. So the problem is, if you're doing a general functional problem, you don't have represent lemma. If you don't have represent lemma, you cannot cast it as a finite dimensional problem, so you cannot solve it in a sense. Of course, you can also do approximation, but it's not a rigorous way of doing that. And another way is doing adaptive lasso. So doing adaptive lasso, the main challenge is here. Well, in adaptive lasso, the main idea is doing L1 regularization, we just penalize on the absolute value of beta j. But adaptive lasso basically states, well, I penalize, say, the absolute value of beta j divided by a weight. And this weight depends on your prior estimate, the initial estimate of beta j. And so you oftentimes, say, for example, you can take it as your least, the absolute value of your least squares estimate. But the problem here, the difference here is, if you think about it in our context, well, in order to get this kind of property, we need to divide by the reproducing Karnel Hilbert space norm of your initial estimate. And your reproducing Karnel Hilbert space norm, if you think about it in just a general additive regression case, then that's going to be the integral of the squared second derivative of that function. And that estimate, generally, in practice, it doesn't work that very well. So actually, many people tried that, and it turns out it doesn't work very well. But actually, on the other hand, a very simple procedure, actually, it has its root in the, it's just the non-negative growth proposed by Leo Bremer in '95. So essentially, you can adopt this idea. And essentially, this idea basically says, well, you can, just like adaptive lasso, I proceed in 2 steps. I first get an initial estimate, but instead of solving this lasso problem again, let's just plug it in, do this shrinkage estimate. I shrink each component and plug it back into a problem. And what's left to do is just for solving this shrinkage coefficient, as I denote here by dj. And this, of course, is just a convex problem in general. So, of course, you can show, basically what you can show, it has, well, one thing I want to point out is in the case of linear regression, this is actually very similar to adaptive lasso, except for in the case of adaptive lasso, you drop this non-negativity constraint. And so basically you get a similar set of results in general, even in non-parametric situation. But here's just one caution. So you use this method if you insist on variable selection. But otherwise, using this type of method, it relies heavily on your initial estimate. So if you get a good initial estimate to begin with, that's a good thing. And how good your initial estimate needs to be? Basically, it needs to be component-wise consistent. So essentially, this tells you, on one hand, this idea of generalized long-life geometry is a good thing, in the sense that it can turn a consistent estimate into an estimate not only consistent in estimation, but also consistent in variable selection. But on the other hand, from practical point of view, it also depends on whether or not you can get a good estimate in the first place. And of course, this is a condition, might be debatable in practice as well. So just to sum up, so basically in this talk, I show that actually many of the techniques actually can be formulated in this unified framework using the tools of reproducing Karnel Hilbert spaces. And of course, this framework, as I mentioned, gives us insight into the connection among these different methods, and also gives rise to new ways of exploring sparsity in other contexts. And so in terms of computation, it in general is just a convex program, but it needs caution in practicing how to implement it, although in principle, it should be solvable. And we showed actually in terms of estimation, this L1 type of spatial regularization will give you a consistent estimate so long as log p is of the order smaller than n. And this holds generally not only for parametric situation. In this case, we show that it also for non-parametric situation. And a selection consistent in terms of selecting the right supporting set is possible for this sparse regularization using L1 type of penalty, but it also depends on your design matrix. And so this is it. Thanks.
Thanks. Yes, Tony.
As always, how to choose lambda?
Well, yeah, that's a very good question. Actually, there are two different answers to this question. So the first one is probably simpler. You look at the theoretical property, as you mentioned yesterday. You look at a asymptotic property, and you can find the optimal range for that tuning parameters. And in this particular case, and go back here. So in this particular case, essentially you want to choose a lambda which is of the order just the same thing as this bound here, and which is probably typical in the case of smoothing splines. Your optimal lambda is going to be of the order as the mean squared error. So this is a theoretical answer, which is a short answer, but in practice, this is a very difficult problem. I think in practice, the universal way of doing this kind of problem probably is just cross-validation. Other methods you can do approximation, but may not always work.
That means your procedure is non-adaptive because in order to choose optimal lambda, you need to know beta.
Exactly, yeah, that's right. But the thing is, if you do cross-validation, of course, this has to be proved. So basically, I would expect if you do cross-validation, you would get similar kind of behavior in general.
So your idea, Tony, would be that if the procedure were to be made adaptive, there might be a log n penalty or something like that on these.
Yeah, and also for this particular sequence model, I just wonder whether simple thresholding works better.
You mean thresholding each component?
Thresholding each component. Because the setting is not very different from wavelets.
Well, actually, I'm not very sure about that, but I think this might be a little bit different from usual wavelet sets. The main reason is actually as follows. In this case, although this sequence model is very similar to the wavelet sets, the main thing, say for example, compared with block thresholding. In block thresholding, because of the orthogonality, you have a closed form for that particular thing. So essentially, you probably have better control of that. And here, the main issue is it's kind of involved in a more complicated way. So it might be the case doing thresholding can help, but it may not be just directly inferred from what we know for wavelets.
Yeah, it might be that related to the so-called the reproducing kernel space. Mm-hmm. One of the things, if you have two questions, number one is that what happens if you go beyond the reproducing Karnel Hilbert space, and like if you go to the more like the inhomogeneous spatial space,
okay.
And the other one might be when you enlarge the space, you might find out that the thresholding and it will have the
you might be
advantage. But if you restrict it to the reproducing kernel space, it's sort of like a smoothing, like a spline, those kind of like, you may not need the thresholding with,
right,
with the smoothing might be good enough to producing the
Let's
optimal rate.
Yeah, thanks.
Is there any further questions?
One more question.
Tony.
So here you have the optimal rate for this particular procedure, take info over all lambda. So another question is, what's the optimal rate if we allow other procedures?
Well, that's actually a very good question. Actually, I have to confess we don't have a good answer to that yet. We are looking into this problem. Yeah, so you're perfectly right. This actually is not a result in terms of the minimax sense. This is in terms of this particular procedure. So basically what we are showing is kind of minimax type of result for this L1 type of sparse regularization. But it's probably possible that you may have different methods that can do a little bit better than this.
There are papers by Inkster and Suslin who give a full characterization of rates and dimension goals among all these things.
Yeah, but here he also has sparsity constraint. Whether that will change the nature of the problem.
Yeah, I think so. Yeah.
Your results about the size of log n versus the size of p are really based on moderate deviation probabilities. So you're assuming that your errors are at least at the level of your theoretical calculations are essentially Gaussian. Okay, so and that, in my experience, that works quite well when your sample sizes are reasonably large, like 20 or so, and p, of course, is much larger still. But when n is relatively small, and p is still, say, no more than polynomially large in n, so when n is about 5, or even less as it is in some genomic experiments, the sort of medium deviation results don't kick in yet.
Yes,
And
that's possible.
in those cases, the bounds for this to work are understandably from the theory and also computable, and also seen in practice, to be much more restrictive than log p less than a constant times n.
Yes, yeah, in some sense it is. Yeah, if your sample size is only 5,
Yes.
yeah, this kind
It
of
does happen.
yeah, that does happen. And in a sense, you can say this bound is still valid because in this case, log p over n is going to be
It's still valid as 5 tends to infinity.
yeah. It's just it's not very useful in practice.
That's right. All right. Yes.
So for the best possible rate over all procedures, do you think we would expect in this probability in the bottom line for those bounds to depend on beta?
For this one here, it's actually
if you were to construct an optimal procedure, would we expect those bounds to depend on beta?
well, of course, I don't have a proof for that, but my intuition suggests actually in this particular case, when p is really big, it doesn't depend on beta. It depends on the dimensionality because you move from finite dimensional problem to infinite dimensional problem. But when p is smaller, I do expect that you have some effect of smoothness.
Okay. If there are no more questions, let's thank the speaker again.